Hi, my name is Owen Redwood, and this lecture is part of the Offensive Computer Security OpenCourseware in 2015, hosted at hackallthethings.com. Today we will be talking about vulnerability research, the permission spectrum, and the overview of the Linux operating system. Root is the most privileged user in Linux, and a lot of jokes and techniques are named after root. Um, And the outline of today's talk is we're going to go over the basics of a system, go over the boot sequence, talk about the rings model and permissions and the least privilege principle, vulnerability research, at least provide an introduction to it, and discuss a lot of Linux topics.
So the BIOS is the ultimate authority of what is and is not installed on a system, typically. You only get one shot at looking at the BIOS when booting up a system. So if you plug something in after that, obviously that requires physical access, you're not going to see it in that initial window. So the boot process is once you turn on the system, the power supply brings all the voltages up to the appropriate levels, and the clock starts cycling and everything synchronizes with it, and then the BIOS kicks in and it does the power on self-test and other tests and checks the CMOS and the RAM settings, make sure it's all clear and good. Then hardware initialization, after if the CMOS is good, it initializes the CPU, the video card, etc. And then it points to the bootloader, and the bootloader provides, depending on the bootloader, provides you with the option to select your operating system that you would like to boot. Or just default chooses the one. So for Linux, the default bootloader is typically in most distributions Grub, although as an alternative, a common one is also Lilo. And when this is started, it presents boot options, and when you select an option, it calls start kernel on the selected option. And this performs most of the system setup, initializes interrupt handling, the memory manager for dynamic memory and other uh, device initialization, kicks off the drivers necessary for the operating system to interface with the hardware. And it spawns the process scheduler, the idle process, and the init process, which is all in user space. And there's a difference between kernel space and user space. The kernel handles all the operating system processes. So the memory management, task scheduling, input, output, which is more than just keyboard, mouse, and monitors. The packets that the network interface, whether it's wireless or Ethernet or whatever, receives. And each one of these inputs, each keystroke, each packet generates a CPU interrupt, which context switches from whatever is going on to handle that keystroke. However, the processors nowadays are very fast, so most users go their entire lives without ever knowing this happens underneath. So it also handles inter-process communication and overall system control. The kernel is typically loaded as a compressed image. This either zlib compressed or bz image uh, formats. And it's important to note that Linux has a monolithic kernel, so most of the drivers that are used to interface with the hardware are all operating in kernel space with maximum permissions. And to that effect, it's important to cover the classic rings model. So this model is very useful for fault tolerance and also for security, because if you have a crash in fault tolerance respect at the kernel space, it can often be fatal. But if you have a driver, say, push down outside with less privilege and it can touch less, perhaps when that crashes, it no longer causes a fatal kernel panic or crash. So that's the gist of it for fault tolerance. And also for security, the diagram on the right illustrates that as you go down in rings, in other words, as it becomes more positive in number, you should conceptually have less privileges. It is important to note, well, I'll get to that in a minute. So ring 0 is typically for the kernel, and this is both in Linux, Windows, and anywhere. And academically, ring 1 and ring 2 are reserved for device drivers, things that could exist in the kernel but are pushed out of it and given less permission, so they risk less going wrong when they screw up, and they're given the least amount of permissions that they need in order to get the job done. Now, the video card may need more permissions than, for instance, the keyboard and the mouse. So, and then in ring 3 is typically where you will find most user mode applications and user processes. So it's important to note that things operate at higher permissions than ring 0. For instance, the BIOS can influence in that boot sequence whether or not one bootloader gets loaded over another, basically determining what operating system you're presented with. System management mode is a security feature that was added on most Intel chips sometime in the last 5-10 years, I don't remember. And it exists as a higher security mode that's overall does good. However, there was some proof of concept work showing that rootkits could be designed to infect this level and provide malicious access at this level in such a way that not even the BIOS would be aware of the system being compromised. And as you go deeper and deeper into the internals of a system, you gain less and less ability to be able to determine whether or not something has been compromised in order for you to find out whether you should reconstitute it or have to remediate it. So with IPMI is Intelligent Platform Management Interface. It's a technology that was introduced 10 years ago into enterprise servers. The motherboard, and you'll find it in almost every enterprise server today. You pretty much cannot avoid buying it. And some of the homework has you reading recent work that came out last year showing just how badly implemented many of the things in it were. So another thing to note is that the original Multics had 8 rings, and there was a special register that the processor used to keep track of what ring each thread was operating on, and when an interrupt would trigger or a thread would switch, it would save that ring, perhaps on the stack or wherever, and then switch to the ring that the next thing was running at. And that's how it would keep track of it. So it's very, very interesting. They took the least permissions model to the max. However, I'd like to cover a more practical model, since ring 1 and 2 are not really widely used, although there are efforts to make the Linux kernel more microkernel-y instead of the monolithic nature it is right now. The useful ones to cover are ring 0, 3, and then the things below it, and then eventually nothing is better than physical access. So that's the extreme end of this spectrum. However, I have something here listed for sandbox non-root user applications, because in order to go from 4 to 3, you'd have to do a sandbox escape, which is not a trivial attack in many cases. I think last year when I covered the code auditing lecture, there was a ton of Java 0 days that were just released the same day. And the first 4 pages of the National Vulnerability Database had various Java virtual machine sandbox escape exploits that were described on it. So it's important to note if you try bringing up ring 4, 5, 6, and other stuff, going down in permissions, people are going to look at you like you're crazy because usually this model is not extrapolated out past ring 3. So vulnerability research relates to this model in its very core, in that vulnerability research is all about pulling off and preventing privilege escalation. Privilege escalation is going from one level of access to a higher level of access. Ultimately, it's all about inverting the model to get to the most privileged state in the offensive manner. So obviously it goes beyond -1, -2, -3, and in theory, having defense in depth means that, especially when each defense adds on to the effects of the previous layer in some sort of additive manner. In other words, I had X permissions in this layer, and then the next layer, which is less privileged, I have Y permissions, and Y is a subset of X. In theory, attacking a system like that should be harder than most systems. Um, However, sometimes you don't have to go from one step to the other. And like I said, the reading for the homework that will be released today shows um, some capabilities in jumping straight from ring 3 to the IPMI mode, which is ridiculously dangerous. So you need not privilege escalate on the same system. There's a technique that spans across vulnerability research, pen testing, incident response topics called pivoting. It's essentially if an attacker compromises a node in your network, they can perhaps use the passwords or notes or established connections on that system to pivot or connect to other systems in your network. And perhaps this allows them to gain access on another node at a higher privilege level. So perhaps they're able to go from a normal user on one system and then pivot onto a root account for another system, depending on how some credentials were set up. Now, it need not be a privilege escalation, as lateral movement is also very useful for attackers and something that incident responders very much have to be aware of. There is no notion of a low-risk system in a network. If you are on a security team and someone says, we don't have to worry about that, that's a low-risk system, I guarantee you if an attacker gets inside your network, there's a chance that they will pivot to that low-risk system that you didn't think to protect, if it can be connected to. And then they can rootkit it, and who knows what happens after that. So lateral movement is something that's very important to be aware of as a defender. And the ways to prevent against this is that the most common technique is known as passive hash. And it was introduced back in the 70s. It's very simple. It's once you compromise a system, you basically get the passwords that are stored on that system or the password hashes, and you can either crack them offline or take the hash, because most passwords are stored in some sort of cryptographic hash, and simply pass it as the input to some sort of authentication protocol. Usually when you log on to many of the old school remote shell style protocols, you would enter in a password, and even for Windows and stuff like that, it would hash it locally and then send the hash over the wire instead of just sending the clear text password over the wire. Now, original attacks against these protocols were, as long as you see the hash, you just replay that packet and boom, you're in. So essentially that is the goal of the attacker here, is to pass the hash in whatever manner it needs to be passed in the, the authentic protocol, and you should be granted access. So the defense against this is to have unique passwords on each system, to not have remote logon or network logon, which is the case for Windows, and to enact firewall rules to prevent and mitigate lateral movement, uh, lateral, sometimes called post-exploitation movement in the network. So this sort of movement can enable eventual privilege escalation on, if your target was target 3, it may be easier to go this route than to just go straight to target 3 and try to find some sort of kernel priv-esc. Because users are usually the weakest link, and perhaps one of the people working on the system all the time has root access and was sloppy. Users are usually the weakest link. So in order to understand this all better, we're going to have to understand an architecture, and the topics that are presented in our coverage of Linux generally apply conceptually to other architectures and operating systems. So kernel space is something that's present in Windows, Linux, etc. And it's much different from user space. There's usually much less you can do in kernel space. And for Linux, things like normal things that you would think that you should have available, like the ability to generate random numbers and the ability to deal with floating point and decimal numbers, are actually much more difficult. And when programming at this level, mistakes are very unforgiving, and crashes here can be fatal and hang or bring down the whole system. Now, modifying the kernel usually requires recompiling it and rebooting from the new kernel to use it. However, there are some tools like ksplice and kexec that allow you to modify the kernel on the fly without rebooting the system. So ksplice allows you to edit it in real time without reloading the kernel, and obviously that's extremely tricky. And kexec allows you to recompile the kernel and hot swap it out effectively. Now, if you're thinking about how an attacker may use these, it would be extremely difficult and unlikely to see an attacker actually using these techniques. Now, as I said previously, once the kernel kicks off, it initializes the idle process, and eventually it initializes the init process, which is the father of all user space processes, establishes and operates the entire user space. So upon init being started, it runs whatever scripts has been provided to set up all the non-operating system services and all of the structures that are needed for the user environment. So spawns the GUI if it's configured to, and then it presents the user with the login screen at the end of its task. So init scripts are usually stored in directories such as /etc/ rc.whatever or rc whatever. And the top level configuration file for it is init tab or init table. So it also checks for something called run level. I don't think I'm going to test on that, so you don't have to pay attention to that. But in practice, it's something that's good to know because it dictates the permissions handling and the permissions model of a user space environment. So init goes dormant after it's provided the user login prompt and authenticated the user, and then kicks off everything and then runs out of things to do. It basically goes dormant and becomes idle, and it waits for the following three things to happen to wake up. Either one of the processes that is started has ended or is dying, or a signal of power failure, or some request to tell it to change the run level. There are other alternatives for init, systemd, or upstart, and these depend on the distribution of Linux that you are working with. So like I said, there are more security layers here. You may be running an application that runs inside of a sandbox, and effectively, root is king. It can do almost anything it wants to the kernel, which then in turn can do anything to the hardware. So it's common to have a single user count per service. So services can range from a web server, email server, and stuff like that. And usually, when set up properly, there'll be a single user count for that service, and that service will be kicked off by that user count once the init starts and all the daemons are initialized and user space. And the user count, if you try to log into it, won't give you a shell prompt or anything like that. And this is an application of the least privilege principle. So let's cover file system behavior real quick. There's a common misconception that when you delete a file, it's gone from the system. In fact, that's often not true. Usually, when you write a file to disk, and this is especially bad with solid-state drives, which I'll cover in just a little bit. When you write a file to disk and you delete it, it doesn't zero out that memory on the hard disk. It provides it for garbage collection later. So you can get to a state like the picture on the right where the first thing that was written was this picture with really smooth legs, and then it was deleted and left garbage collection, and this picture, the feeling of having, was written next, and you see how some of the rest of this block has the previous picture, and then this was deleted, and then eventually this starts getting written, and the file system will know that, okay, this file ends here. You know, it doesn't go all the way to really smooth legs. But if you look at the disk in a raw format, this block, it will have all this data. So when you delete stuff, the data does just get left on the disk until it's garbage collected, which may happen at any time, and the inode is just unlinked. So we'll cover inodes in a little bit, but for solid-state drives, there is a common implementation to provide wear leveling to expand the lifespan and get the most out of the device, because solid-state drives only support so many writes to each sector. And so what happens in solid-state drives is that when you load a small file and you make a single change, you would think that to be efficient is, say, if I only write a byte or whatever, I'll just go to that original sector and update that byte or 2 bytes or whatever. Instead, in most implementations in solid-state drives, it takes everything that's been loaded and writes it to a new sector, no matter how small the change is. And so if you go to delete the most recent version of a file, a previous version on the solid-state disk will probably be present. In fact, you'll probably have a scattered look at the entire version history of that file, which is very interesting to consider for security reasons. So this is the basics of a file system, basically derived from the fast file system, which is one of the original Linux file systems. And many file systems derive most of their behavior from this implementation. So what I have here is this dotted line denotes what is definitely on disk, and what is above it is usually stuff that's being loaded into memory to enable the efficient navigation of what is on the disk, because it's not so cleanly laid out most times. So what we have are directory entries, and they have file names, and that's typically what most users see. That's all they're exposed to. But underneath, there's something called an inode, and then there's an inode table, and they point to blocks, and there's indirect blocks, and there's the metadata and the inodes, which also the users get exposed to, and it gets complicated. So when the file system is initialized, the directory entries are loaded into memory, and the inode table is usually also loaded into memory, although it can operate purely off disk. That is a slower implementation, however. And for each directory entry and the files that are in it, there's an inode table entry. This inode table entry points to the specific entry in the inode table, and that entry has lots of metadata, such as the last time this file was accessed, the size that this takes up on disk, so on and so on and so on. And then there's also permissions metadata, like the user ID that owns it, the group ID that has access to it, and whatever permissions that they are allowed. And then the important stuff is the blocks, and for each file it basically denotes this is the first block, this is the second block, and it provides the file system with exactly where it is on disk. And so on and so on and so on, but there are only 15 4K size blocks in each inode, so an indirect block points to basically another set of addresses that describe even more file content, and these can point to more indirect, and it basically forms a linked list. So there's nothing preventing a system from having two file names that point to the same index node, and if you take, in general, what happens when you delete a file, this just gets unlinked. The inode entry will still remain intact, and the file content will still be there on disk. They will be marked, especially this, for garbage collection, and eventually the memory inode will go away. But the data is going to remain on disk. So in the case where you have two files linking in the same inode, and you tell it to delete file X, well, you can still use file Y just the same. So that's also very important to consider for forensics and for security in general. If you're trying to securely delete sensitive information, this is something very important to consider. Linux utilities like Shred offer secure deletion services. However, like I said, there's problems in securely deleting anything from a solid-state drive. There has been some very useful research coming out of the FSU department from a previous PhD student, Sarah Giesberg, on secure deletion at this level, and I believe some vendors are starting to implement her algorithm. So now that we've covered how the file system works, let's cover the generic directory layout for Linux distros, and this is often one of the most confusing things for students, as it can vary per distribution of Linux. It's not really something that is standardized, and that causes more confusion, and we're going to cover the most interesting places. So CD is the utility or the common command line tool to change directory, and if you tell it to go to the following destinations, I'm going to explain what happens. So if you tell it to go to slash, this denotes the root directory. And this is where the file system begins. It is the root of the file system. Every other directory is underneath it. And it is not the same as the root account, and it is not the root account's home directory. So /etc usually stores the config files for a Linux system. So the config for all the services, all the applications, anything you can run. Effectively, if it has a config file, first place to look for it would be in /etc. And they're mostly stored in text files that can be edited by hand. Well, by your favorite text editor, rather. /bin and /userbin usually contain most of the binaries that when you run an application, this is where the machine code will be stored for it. And the /bin directory contains the most important programs typically for systems, such as the user shells, file system tools like ls, regular expression tools like grep. User bin contains other applications that aren't so common for users, but there's no real clear distinction between the two, and nothing prevents you from putting your applications wherever you want, and that is really at what's at heart in Linux and similar systems, is that they are fully configurable. You can do whatever you want with them. So there's a difference between SBIN and user SBIN, and usually they are used for system administration programs, and SBIN is where the most common ones will be, and user SBIN are where perhaps the custom ones will be. And then /user stores most user applications and their source code, and any pictures, documents, or perhaps configuration scripts or files that they may use that aren't already located in /etc. It is important to note that this directory is usually the largest directory on a Linux system. And /lib is where the shared libraries and shared objects for the program are located. Sorry. So if you're not familiar with the concept shared library, they're similar to dynamically linked libraries in Windows, if you're more familiar with that. And so when you compile a program, you can either compile it statically or dynamically. I'm not sure if I covered this already. If you cover it statically, say you use in C standard lib and standard IO, it's going to take the compiled libraries for those code and load it into the binary and then provide it all as a standalone. So you can run it on any system even if it doesn't have those binaries present. The result, however, is a very, very large file. So the alternative is to dynamically link these applications when you compile them. And the assumption is that wherever you run them, it'll have those shared objects or those libraries present, so that when you run it, the linker and the loader will find the shared object and load it into memory when you run it, so it doesn't take up so much space on the file system with all the redundant libraries being stored here and there. It also makes it better for dealing with upgrades. Say you upgrade to a new version of C, and then it comes with all these new libraries. If every application you had was statically linked, well, it's going to have static versions of all those older libraries and shared objects in them, and you're going to have to recompile every single one of them to update the whole system. So that's just an illustrating example. I don't think anyone actually statically compiles every single thing. /boot contains the boot info. The Linux kernel is kept here, and that is usually going to be the VM linuz file. That is typically the kernel. /home is where all the users' home directories typically are, and with the main exception of root, every user has a directory under home, and it's where all their files are stored by default. /root is the superuser or UID0's home directory. Instead of /home/root, it's just /root. /var contains the frequently changed variable data when the system is running. It also contains logs, which is very important for security and also important to attackers for them covering their tracks. /temp is the scratch space for temporary files. /dev contains all the device info for a Linux system, and it's important to note that in Linux, devices are treated just like any old file. And for the most part, you can read and write to them just like a file. depending on the device. Slash mount is used for the mount points, so if you plug in a USB thumbstick or a CD-ROM or an external hard drive, it's usually going to be mounted by the file system in this location. It depends on the distribution of Linux, though. So slash proc is a very special case. It is a virtual directory and does not exist on the file system. It is a construct of the process scheduler of the operating system, and it contains info on the kernel and all the processes. So it contains special files that permit access to the current configuration of a process in the system, and for certain security aspects, it allows you to configure ASLR, for instance. We'll cover that later. It stands for address space layout randomization. And it allows you to see exactly how the memory is mapped for a process, among other interesting things, as well as for that memory map, the permissions for each segment in it. And we will be covering this in the exploit section. So, with that covered, we now have to cover permissions and how they're handled with users and groups. And file permissions in Linux are really defined by three categories. For each file, you define the permissions of the file's owner, or the self. Then the file's group members, or the groups of the owner, and then everyone else. It's not as fine-grained as it could be, but this is the universal way of doing it. ls-l will show you the file attributes, not the extended ones, but the file attributes and the permissions of files in a directory. And chmod stands for change. It basically allows you to change the permissions, to modify them. So chadder is different from chmod, and lsadder is different from ls. They influence and allow you to see the extended attributes of a file, and those are important to consider. I do believe I covered them in a little bit. chown changes who owns the file, and chgroup changes the group of the file. So the most commonly talked about file when talking about permissions is the etc password file, in that the etc password file contains, for every user, the user ID. In old implementations, it would contain the password hash and info. It would contain the user identifier, the group identifier, the user's home directory path, and the default program when the user that launches when the user logs in. And the entries typically are colon delimited and look like this. May have other metadata like room, phone number, etc. And in more modern distributions of Linux, the etc shadow file was designed to actually store the password hashes. So usually in most modern systems you will find that instead of a password hash here, you'll find an X, which denotes that the password hash is actually stored in the etc shadow file. So the distinction really is that the etc password file is readable by all. So if I compromise a system and I can read the root password hash, that's a problem, because I can then crack it offline later and use it to log in as root, which is a serious privilege escalation. So many user-level applications actually had to be able to find out who the other users are, like finger, perhaps find out what my home shell is, what my home directory is, and other stuff. So actually there are legitimate uses for other users that are not root to read the etc password file. So instead of storing the password hash here, it lists an X to tell the system if you're looking for a password hash, it's in the SE shadow file, which is only accessible to the root user, which solved that problem. So you can no longer get the password hashes just from any account. So to see the options for storing the password in whichever hash format you like for system, man3crypt is the command you would type to show the encryption manual, and it would list the options. Typically, the options range from MD5 to SHA to DES, perhaps Blowfish in certain systems. It's important to note MD5 is no longer secure. DES is also considered no longer secure, but it's the default. As far as I know, this slide is a little old. But it is not so bad if there's salt. And I'm not going to get into salt because I think these topics are very well covered in other classes at this university, and I'll leave it to them. So salt is used to perturb the hash and make it harder to crack. DES is less secure than triple DES. I believe with a custom FPGA array, even the strongest DES hashes, even salted, can be cracked in a matter of 24 hours. So I've talked a lot about this thing called the least privilege principle, and effectively this principle embraces the notion that every process, every user, everything must be able to access only what it needs to and nothing else. It is only given the very least for it to do its job and for it to sufficiently do its job. So things like having a single, no long gone user account for services, so that if you compromise a service, it's not so easy to just spawn a shell, or pass commands up to a system shell, rather. Things like jails, things like sandboxes, these all provide for security in depth and add on to the rings approach. And they often also make logs clearer, because if you just have root running everything and you share the root account with 5 other people, it's hard to tell in the logs which person screwed something up. So let's talk about jails and sandboxes real quick. chroot is one of the most common utilities for doing virtualization or sandboxing, and really the trick to chroot is that it's given a new directory as an input and also a process to spawn. And what it does is when it spawns that target process, it tells it the provided directory is actually the root of the file system. So if it tries to change its directory all the way back to root and do something, it's instead told that no, this is root instead. So that's stored in the process space, usually on the stack, I believe. And what results is a jailed process that can't access resources like the etc shadow file, the etc password file, in a normal manner. So in order to break out of this, you have to break the chroot jail. And if you have arbitrary memory rights, you can tell it and know where that value is stored in memory. You can tell it the new value you'd like for a root to be, which is interesting. So there are lots of other utilities for sandboxing and providing operating system level virtualization. And I'm just having this slide to illustrate. chroot is seen as the dumbest and the least useful. It is useful to to look at some of these columns like disk quotas and memory limits and CPU quotas and whether or not it's isolated on the network, whether or not it's isolated from root privileges. So certain virtualization techniques allow you to have all these if it's properly configured. So like memory limits, if it limits the resulting process's ability to take up memory, you can prevent many memory exhaustion uh, attacks like fork bombs and stuff like that, which also affect CPU quotas. And network isolation can prevent something from doing that IPMI direct attack that we've discussed a little bit, and so on and so on. So there's many fine-grained approaches that are out there. Is the main point of this slide. So continuing on the discussion of permissions and privileges, let's now consider, since we discussed file permissions, which are self, group, and other, the set UID bits, the set GID bits. So the set UID bits for a file denote what user this should run at if you execute this file, if that file has executable permissions. If you try to execute a random text file, well, it's not going to be recognized by the processor as having valid machine code instructions. So for the appropriate files that are binaries that have executable permissions, if a set UID bit is set, it's going to tell the system to run that binary as the binary's owner instead of as Bob or whoever decides to run it. So this provides a brief escalation of privileges to a different user so a task can be performed, which does have legitimate uses. For instance, changing my own password requires accessing the etc shadow file. However, I don't need to be root. I shouldn't need to be root in order to do that. So the password binary is set UID as root, and it performs a very singular task, and then it de-escalates permission when it's done, and returns back to the user having changed their password, and it's done. So you don't want to just let anyone do this freely, and there's tons of other applications of this, tons of other examples of this application. So setGID is very similar. It denotes what group ID this should be run as when you run a binary. And other two things to consider is that when a process is running, the effective user ID is the UID number. So if you have, for instance, run password to change your password, while that's running, it will have UID of 0, which is root. And then when it's done, it will return to you. And so, however, the real user ID, your username, will still be the same during the execution, I believe. So anything that's set UID as root has root privileges, and most attacks in a Linux system, if they gain initial access, will involve doing reconnaissance to see if there's vulnerable versions of set UID programs and including these in the attack chain as they are single points of failure. So these are examples of things that are set UID binaries. We've covered password. Sudo is another obvious one. However, things like ping may not be so obvious as to why they require root access. The main explanation for that is it requires access to the network interface, not just the standard socket calls that are provided by C, but it needs a lower level access in order to do the ICMP handling, which is the Internet Controlled Message Protocol. in order to do pinging. And so on for ping 6, which is IPv6, and ARP ping, and so on and so on. So anything that requires a lower level of access is typically handled in such a manner, such as mounting file systems and unmounting them, such as changing user. Obviously, that results in whatever user you're changing to and authenticated to. However, in order to do the authentication, that process needs access to the etc shadow file in order to see whether or not the user's entered password matches the hash stored for the target user they want to change to. And so on and so on. So, in thinking about the attack surface for a system for just privilege escalation attacks, the following categories would make up the chunk of the attack surface. The set UID privilege escalations attack surface, which is basically any binary that has a set UID bit and is owned by root. Kernel privilege escalations, and as we covered in the code auditing lecture, those vulnerabilities and those bugs can't exist in kernel code, and kernel is written mostly in C, so that's where it's extremely relevant. Daemon exploits or root process exploits, anything running at root that can be interacted with that perhaps has a vulnerability. And again, as always, weak passwords if the root password is not set, or if it's set to something terribly weak, that's also considered in the attack surface, and so on. I guess as a side note, it's important to note that set UID and set UID on directories act entirely different. Set UID does nothing on a directory. It's usually disabled or that's an invalid operation. And set GID, however, makes it so that any new files, any new subdirectories, and anything recursively inside it all inherit the GID provided. So let's get to some alternatives to the privilege, the permissions model for standard Linux distributions, and talk about alternatives. Access control lists exist, but they are disabled by default. They extend the owner group other access model to specify on a per person, per user basis what permissions they should have. So it is an aspect of the file system, and it depends obviously on the file system. And you can turn it on. It's a mount option in the file system table file. So on Debian systems, it's something that can be apt to get installed. It's effectively called ACL. That's a command line one. There's a GUI-based one, EICIEL, and basically an example is, say you want to have two groups to have access to it and also a different user, say the CEO or someone very important in an organization, and you may want to have two groups to have access to it, but you want to have the two groups to have different levels of access. So you would say, for instance, set for the developers group, you want them to have read-write privilege on this target.txt file. And say for the quality assurance group, you could have execute this as just, let's change this. It would be this. There we go. If you just want to give the quality assurance group permission to execute it because they're just going to be running it, you would do that and say you want Joe, the CEO, to have just read-write, and you would do that. So it's pretty straightforward, and something to note is when you do ls-l to see the common file attributes and the common file permissions, if something has been set up with access control list, it will have a plus sign at the end. That's one of the only ways to determine whether or not it has it at first glance. So, as I mentioned earlier, there's this thing called CHAtter, and it influences the extended file attributes. And these aren't present in every single system, but they cover very important things that are useful for system security. Um, CHAtter plus A makes the file append only, which is great for logs. Because if I'm an attacker and I get access to your system, I'm going to want to, in general, destroy any evidence that I was there, especially if it's a system that's going to be looked at by an incident responder. It makes it harder for the attacker to get in trouble, and if you can destroy all the evidence, all that tangible evidence that can be used in court is now has to be either if it's happened to get written from memory to the file system, has to be forensically retrieved or is completely gone. So if you make a file that append only, it makes it so that an attacker or a user can't just delete it and flush the logs. However, they have to also be prevented from doing chatter minus A, which does the reverse of this operation. It makes it no longer append only. Likewise, there's an option to make something immutable. It means no one, not even root, can change this file or delete it or link to it. It is completely immutable. In a competition, I once trolled the other team with this, and it was a pretty useful trick. They had no idea that this option existed or chatter could be used in this way. They had root privilege on the system, but they weren't able to change the permissions on some file or read it. They weren't able to do anything to it. They were just scratching their heads the whole time, not knowing that this secrets file that had just gibberish in it was chatter plus I. Secure deletion is also an option for extended file attributes. However, it kicks in a standard algorithm that's provided by that operating system or that distro to do secure deletion, and it may not have support for solid-state drives and other stuff. It's important to note that only the root user by default can use extended file attributes, and it is enabled also in the file system tab file. So this is a little unorganized, bear with me. The TTY stands for a terrible acronym, teletypewriter, and it comes from older systems and original work in computer science, and the origin of it really has to do with serial port terminals and very rudimentary terminals that were just basically streaming characters over high and low wires to the system and to the monitor that the user was commanding it over. And really, there was no GUI environment back in this day, and all you got was the standard old DOS prompt or command prompt. And effectively, when you log on to many Linux systems, if they're not configured with a GUI, this is the first thing you will see. The practice still stayed. And, there are basic commands that are present in most terminals, like who. You can also switch to another terminal, which is chvt, but that requires root. And PTSs came about, which are pseudo terminal slaves, also a terrible acronym. And it is essentially a terminal that's emulated by another program. So it emulates that streaming character application which is a bit complicated. So if anyone's touched a Linux or a Mac system, they've used this. So things like Xterm or even SSH or Screen. All of these are basically emulating terminals. And next topic is going to be daemons. So the way to view daemons is via the service command, and that should be present in almost all Linux distributions. They are typically backgrounded processes like an SSH host or the system log daemon or the web server, which may be HTTPD, and et cetera, et cetera. Almost all daemons are spawned by that init process, the father of all processes. And the standard implementation behavior is that they have no controlling terminal, so you can't pass commands up to the terminal from the application. And they ignore all terminal signals except for terminate. And they have no open file descriptors. They're dissociated from process groups. And they have very limited permissions down to what they just need to do. Also, commonly, they have a user account that is tied to them and that spawns them through init. So another thing that's useful to cover that are somewhat close to daemons are kernel modules. And these modules effectively contain code, are basically libraries and executables that can be loaded by the kernel, and they extend the kernel to perhaps add support for new file system, or adding system calls, or for a wireless driver, or etc. And it is a very convenient method for modifying the kernel. However, it can be abused by attackers, and it's something that's very important to be aware of. Cron jobs are also important to be aware of because it allows for things to be run at a regular interval. Perhaps there's a system administration task that needs to be run. And what I'm getting at with daemons, with loadable kernel modules, and with cron jobs here is that these are avenues for attackers, once they've compromised the system, to maintain persistence on that system. Say that system goes down for a reboot once they've got access to it. They're going to have to come back in over the network and re-exploit the system to get access again once it's been rebooted, unless they've added in some sort of back door to the system that allows them easier access, or that pings back out once the system is loaded. For instance, that's how botnets work. So, cron jobs are time-based jobs in Linux that enable a user to schedule a job at any time, whether it's to run some sort of command or to run some sort of script. And they're commonly used to automate system maintenance or administration, but they obviously can be abused. And so if you are dealing with an attacker and you find a system might be compromised, it might be helpful to go through the previous commands that have been run if they haven't cleared the history. And for an attacker, however, it might be useful to try and repeat previous commands, and the bang for bash and other terminals, bang style commands allow you to repeat the previous command for bang bang, and for bang SSH allow you to repeat the last SSH command. And so if you append it with :p, it takes whatever was run last that's matching this and prints it instead of running it. And so similarly, instead of just command line logs, there are tons of logs that can be used for forensics and figuring out what an attacker did to the system. But these are also targets for attackers to clean up their tracks, so you don't figure out what they've done to perhaps harden their access on the system to maintain their foothold in your network to continue doing bad stuff, or to prevent you from figuring out what they've done and they're already gone. Um, so these are typically stored in /var/log, and so the most common one is messages, and that's just the generic messages. However, ones that are useful for authentication are auth.log, fail log for failed logging attempts, and last log for last logging attempt and activity. The boot log, system log, etc., etc., etc. Usually daemons will have their own logs. For instance, MySQL server and web servers, etc. So like Apache 2. And also for intrusion detection, there'll be firewall snort and stuff like that. Virtual machines will have their own logs. And there's, depending on the system, perhaps a GUI-based log viewer for your distribution of Linux and your desktop environment. So things that attackers do, like brute forcing and SSH over SSH, leaves a very large footprint in the logs. You'll see a failed attempt for each attempt. A failed attempt logged message for each attempt that the attacker makes. For each successful login, you'll see the IP and the domain that the person connected from to your system. You'll see any messages regarding modification of the system, modification of the kernel, loading or unloading modules, any changes to daemons, and things that may be part of the network and not necessarily part of that system involve also firewalls, gateways, traffic logs, and these may log every single packet that's gone over the wire for perhaps the last 30 days or so. So I believe I emailed out a paper to the class encouraging you all to read it, and this is something to consider in the calculations that the authors made. Also, there's Active Directory, lightweight directory access protocol, secure copy, file transfer logs, and directory sharing logs. And which brings us to firewalls and how attackers are kept out. Firewalls do work. They are effective defenses. They are very also straightforward. Firewalls can be host-based and network-based. We're going to cover host-based firewalls and cover what is provided by default in Linux and also specifically Debian Linux. Most Linux host-based firewalls rely on this kernel-based system called netfilter. And IP tables is the user space tool that interacts with netfilter and manages it. So netfilter is really just a framework within the Linux kernel. It has 3 standard tables: filter, nat, and mangle. So it is primarily just a connection trafficking system, and it does not do any filtering itself. It just provides the framework to do it. So filter has 3 different chains that are a part of it: input, output, and forward. So it allows you to filter incoming packets, outgoing packets, and packets that are being forwarded perhaps to a different interface. And this is the one that is primarily responsible for system protection. So NAT, if you haven't taken a networking class before, is network address translation. It allows for subnets, and it's basically the main reason why IPv4 is still alive today. So its main chain is masquerade and allows you to translate from one IP space to a different IP space. So for instance, the global IP range to the subnet IP range, which most people think of as just 192.168.1. whatever their router assigns them, right? The last one is mangle, and it's for changing certain packet fields prior to local delivery. Some IDPS systems do mangling to mitigate exploits if they detect them. and that's interesting, but it's also very, very prone to false positives and messing up stuff. So IP tables have been part of Linux since the 2.4 kernel. So, like I said, there's tables, chains, and then there's basically matches. So basically, there's rules, and if something matches, it kicks in, and the target is enacted. Um, so policies are built from an ordered set of rules, and it's a linear list. It just starts from the top for each packet and goes down. So if you want to prioritize something, it's just you put it above the other thing you want it to take precedence over. And so each rule is applied to a chain within a table, and obviously depending on where it's going dictates the chain. So for IP tables, there's an addition of the fourth table, which is called raw, and it operates independent of NetFilter. We're not going to cover it. It's tricky. So for instance, for the filter table, the following chains are going to be input, output, forward, and I already covered this. And this is a good diagram. This diagram comes from the book Linux Firewalls by Michael Rash. And so above the dotted line is user space, and below it is kernel space. And this is effectively what's going on in NetFilter and IP tables is basically doing this. So when incoming packets come in, there's NAT pre-routing chain. So that dictates if it's coming over the interface for global IP space, what to do with it, and as a routing decision, is it input, or are we forwarding it? So if it's forwarding, if there's NAT post-routing rules that apply to it, maybe we're now translating it to the 192 address space, the subnet space, we then change the IP accordingly. Maybe that's the case, or perhaps there's no NAT at all, and it's just part of a network. And in such case, it would do the same thing. The incoming packets would come in, it would look for any rule matching it in the NAT pre-routing. If there's none, keeps going. Now, it's a routing decision. Is it input to this system, or are we forwarding it to another system? Say it is input to this system, and so we enact any filter input rules there might be, and we provide it to the local socket. The local socket may accept the connection and start talking, at which point outgoing packets go out accordingly, and they're looked at by the filter output rules. And if there's anything that matches with them, those rules are enacted, and so on. The NAT post routing is enacted if there's any rules that match, and so on and so on. It's relatively straightforward. So each rule has a set of matches along with the target, and the target tells IP tables what to do with the packet when that packet matches the rule. Pretty simple. So you can match based on the source, based on the destination of the packet, based on the protocol, based on interface, state, or based on a string that's present in the packet. So targets basically is what you do with the packet. Can be accept, in other words, you allow it to continue. Can be drop, in other words, this looks malicious, or this matches recent signature of vulnerability advisory, and we've decided to add it to our firewall and drop anything matching it. You may want to use drop target to do this. Or for things that look suspicious, you log them, and it logs it to syslog, the whole packet. Do you reject it, or do you return it and it sends a processing packet? It depends on the implementation. So, in general, any system behind a firewall should be able to initiate things that are pretty standard to normal operation out to the outside world. So DNS queries, if you don't already have an internal DNS, SSH, web traffic, etc., and anything that's not standard should in general be prevented from reaching the outside world, because in the past it has been very, very common for malware to use non-standard ports for various reasons. Um, so there's also a useful practice called stateful packet inspection, and it basically tracks a how a connection and traffic in it follows the state machine for that protocol, for instance TCP. And anything that doesn't fit within the state machine, the connection can't get killed or get logged or whatever. And it does add a layer of security to prevent denial of service style attacks on systems that perhaps don't have the most securely implemented network stack. And for any given system, in order to determine what you may need to let reach the outside world, the etc services file contains all the network port names and numbers which can be used to determine the firewall rules for a system. So that's it for the lecture. The important thing to keep in mind is if an attacker gets root, they can do anything to your system, and it's one of the most important things to protect, and obviously access to the lower underlying system. So homework 3 will be released later today. Homework 2 is going to have a correction announced for it later today, and it's going to be extended till Saturday at midnight. Send any questions to me if you have them. All right.